So in this lesson, we'll try to understand friction and how a better understanding of it will help us tackle problems in mechanics a lot better. So let us say you have a mass M sitting on a table, and we know that it will put a certain force on the table which will be equal to mg in value, and we know that the table will also push back the mass in the upward direction, and its value would be also mg. But we call this normal reaction, and it will be equal to mg because we know that the mass is not moving in vertical direction, it's not moving in y direction, so n has to be equal to mg. Now let us say you push this mass with a certain force F. Let's label the force here as F. And let us say in the first instance the magnitude of this force is, let's say, 10 Newton. And what you would see is that the mass would not move. And why it doesn't move is because there's a force of friction which is opposing the force you are putting on the mass. So the force of friction would act in the opposite direction. Let's show it over here like this. So this is your force of friction. And whatever force you impress, if you put a force of 10 Newton, the force of friction, let's call it F. The force of friction would also be 10 Newton. Let us say you increase the force. You increase it to, let's say, 12 Newton. What will happen is the force of friction will also increase to 12 Newton to oppose the force you are putting on the box so that the box doesn't move. Now, let's say you decide to take up the force to 14 Newtons. The box would still not move because the force of friction would now have increased to 14 Newton. But let's say there would be a time when the box will actually just about start moving. So let's say the force required to just about move it is 15 Newton, or let's say 15 Newton is a force where any decimal increase in the force would just about move the block. Then the force of friction would also be 15 Newton, and we would know that any force above 15 Newton, so if you put a force of 15.000001 Newton, the box will just about start moving because the force of friction is just not able to keep up, and the box kind of breaks loose and starts moving. So what we say is that this maximum force is the static force of friction, which equals mu into normal reaction. We write it this way: F max would equal static coefficient of friction into the normal reaction. And this is the maximum force beyond which the box will start moving. And once the box starts moving, there's a different coefficient friction, and we call it mu k, or the kinetic coefficient of friction. Kinetic pertaining to movement, static pertaining to the mass being still or stationary. And mu k is always less than mu s. And it's quite intuitive. If you try to push a table, you know that the initial force required to push the table is more than the force required to keep the table moving. So once the table starts moving, you would realize that the force required is less. And that's the reason kinetic coefficient friction is less than the static coefficient friction. Now, it's easy to find mu s. How it is found is that you take a block of, let us say, mass m, you put it on an inclined plane, and you kind of crank up the incline, you increase the angle to a point where the box just starts about sliding down. So let's say that angle is alpha when the box just about starts moving. And let us say the situation is something like this. This is your angle alpha at which the mass has just about started moving, in which case the forces acting on the box are 1 mg acting in the downward direction, and if you resolve mg into its component, what you'll find is you'll get one force in this direction and another force, what you'll get would be in this direction, so that the sum of these forces is equal to mg. So let's go ahead and label these forces. So this is one vector over here, and this is your other vector. And you would know from simple geometry that if this is angle alpha, this would also be alpha, in which case this force would be mg cos alpha, and this force here, this one over here, would be mg sine alpha. Now, what you would also intuitively know is that since the box is not moving, there is a force of friction which is stopping its motion and it's acting in the opposite direction. So let's go ahead and denote that force as this. Let's say it's the opposite direction, and since it is just about to move, it means it is F max over here, what you've just calculated, and let's label it as F max. So given this situation, we'll go ahead and apply Newton's second law of motion, where we say that the net force acting on an object is equal to its mass into the acceleration. So if we assume this as the x-axis, if this is the x-axis, and we assume this as the y-axis, taking positive in this direction and negative in this direction, so let's say this is positive and this is negative, then what we can say is that there's one force acting in the downward direction, which is mg sine alpha, and we'll keep it positive because in the positive direction, and the other force is the force of friction, which is acting in the opposite direction. Let's therefore write it as negative F max, and this should equal mass into acceleration. But we know that there is no acceleration, the object is stationary, it's just about to move, so this component becomes 0, and what we get is F max is equal to mg sine alpha, and we know that F max, we've just found earlier, F max is equal to mu s into n. So we'll put mu s into n is equal to mg sine alpha. Here the normal reaction is nothing but mg cos alpha, because you see this box is pressing against this inclined plane, and therefore the normal reaction would be in this direction, and it'll be equal to mg, because you can see that the box is not kind of going into the inclined plane or flying off the inclined plane. As such, there's no movement in the y direction. Therefore, the normal reaction n should equal mg cos alpha. And if this is the case, we can say that mu s into mg cos alpha is equal to mg sine alpha, and your mg cancels, and what you get is mu s is equal to tan alpha. So we can say that the coefficient of friction, the static coefficient of friction, is the tan of the angle at which the object just about starts moving. Now, one interesting thing you would have seen here is that the coefficient of static friction is independent of the mass. It's actually dependent on the nature of the two surfaces. So let's say if this is a wooden block on a leather incline, then mu s would be relevant to these two surfaces. If you had a wooden box on an iron plane, then mu s would be relevant to these two surfaces.